Good day and welcome back for the third part of our discussion on the definite integral. In our previous videos, we've defined the definite integral, discussed its interpretation, and worked through a typical example. In this video, we will continue on the conversation by investigating some additional commonly encountered examples. So the first is to look at this definite integral from 0 to 3 of the function x minus 1 and evaluate it in the two possible ways. We can interpret it geometrically as this net difference of enclosed areas, or we can use the definition of the definite integral. And luckily for us, we're going to interpret it or evaluate it in both ways. So in terms of the geometric interpretation, we need to start by sketching a graph. So the graph of the function y minus 1 would be made up of a line with y-intercept minus 1 and slope 1. So at 0, it hits minus 1, and at 3, its output would be 2. So roughly speaking, it looks something like this. And pretend for me that really looks like a line. When it comes to evaluating the definite integral of this function, remember it's this net difference of enclosed areas. We see that we have this triangular shaped region, let's call it area A1, that sits above the x-axis. And then we have another triangular shaped region with area A2 that sits below the x-axis. So the value of this definite integral is simply A1 minus A2. You know, both of these areas are triangular. So to find A1, we use the formula for the area of a triangle. 1/2 base times height. Similarly for A2, 1/2 base times height. So the value of this definite integral, if we simplify this a bit further, 1/2 times 2 is 1, so we end up with 2 minus 1/2, or the value of the definite integral is 3/2. And once again, we can see graphically from our interpretation, it certainly appears that the value should be positive because more area is enclosed above the x-axis than is enclosed below the x-axis. The second possible way for us to evaluate this definite integral would be using the definition. So note the definition of the definite integral, if we just write out precisely what the formula tells us, would be the limit as n goes to infinity of the Riemann sum, which is from I equals 1 to n, of f of x sub I delta x, where we know precisely what these quantities are. The function of interest is x minus 1. Delta x is b minus a over n, which is 3 over n. And x sub I is equal to a plus I delta x. So we'll say 3i over n. So substituting in these quantities, we have the limit as n approaches infinity, the sum from I equals 1 to n, and f of x sub I. So in our function f of x, we would like to replace each of those x's with a 3i over n. So that would give us 3i over n, our x sub I, minus 1, times delta x. And this should be starting to feel like a familiar process, as it's the exact same thing we were doing in the previous section when we were finding enclosed areas. So proceeding as we've done before, we want to algebraically simplify so that we can potentially break the sum up and apply our common formulas. So distributing through the 3 over n, we're left with the limit as n approaches infinity, the sum from I equals 1 to n, of 9 over n squared times I minus 3 over n. And note this process should be starting to feel more familiar, certainly, but also more efficient. Once we get it here, the objective is to take this summation and break it up over this minus sign, and then pull out constants. That is, we can pull out the 9 over n squared, have a sum from I equals 1 to n of I, minus 1 over n, the sum from I equals 1 to n of 3. So we've simply broken the sum up over that over the addition or subtraction in this case, pulled out constants. We just as easily could have pulled the 3 out, but we did that in a previous example, so I went ahead and left that constant, in this case of 3, inside. We can handle it just as well in either case. Now, applying our common formulas, and these are things we should certainly be familiar with, the sum from I equals 1 to n of I is n times n plus 1 over 2, and the sum from I equals 1 to n of any constant is that constant times n. So note, if we want to do some cancellations, we can say n and n cancel, n and n cancel. So in terms of evaluating this limit, it's rather ideal. The first part is a rational function in n, 9n plus 9 over 2n. The degree in the top and the degree in the bottom are the same, so you simply divide those leading coefficients. So 9 halves, and the limit of a constant such as 3 is just itself. 9 halves minus 3 is 9 halves minus 6 halves, which is the 3 halves that we got a moment ago. So a big sigh of relief. We evaluated this definite integral using our two potential methods, and in either case we came up with the same answer. And let me just note, as we have previously, when it comes time to homework or exams, you do have to pay particular attention to what the question is asking you. Specifically, if you're asked to use the definition of the definite integral, that really means you need to start off with this limit of a Riemann sum. If you are requested to do that and you do not, then you will potentially lose a large majority, if not all, of the points for the problem. So be forewarned. And moving on to another common example, which involves being given a limit of what looks like a Riemann sum and asking us to determine a region whose area is equal to this limit, which is how we would have asked the question in the previous section as well. So I just as easily could have asked you for a definite integral whose value is given by this limit. So intuitively, I'm thinking that this is representing a definite integral of a function. So what we need to do in this problem is find or determine a, b, and f of x. So what function is enclosing the area between what values of x? So reminder, when we had this definition of the definite integral, this is really the limit as n approaches infinity of this Riemann sum. And hopefully we are remembering these a bit more quickly now. Delta x is b minus a over n. X sub I is a plus I delta x. So this is going to be a purely pattern recognition type of problem. So based upon pattern recognition, it looks as though we have our delta x, a constant over n, which means this remaining stuff multiplied by it should represent our function f of x sub I. So let's just kind of make a few notes and see where it leads us. Delta x is 2 over n. And that is telling me that in this case, this 2 is b minus a. That doesn't determine for me what b and a are going to be, but it will give me something I can come back to in a moment. So what else do we have? F of x sub I appears to be 1 plus 2i over n cubed. So my guess from looking at this is maybe f of x is cubing, and this quantity being cubed would be our x sub I. So if x sub I is 1 plus 2i over n, this 2i over n is the I delta x, which means 1 is equal to a. And that does it for us. Note if we have a is 1 and b minus a is 2, that determines b. So putting this all together, and I'll make a little side note here. If a is 1 and b minus a is equal to 2, b would have to be 3. So our conclusion should be some type of statement explaining what we've found. A common mistake is often doing all of the work like we've done here, but not really given a clear response. So the area enclosed under the graph given by the curve y equals x cubed above the x-axis between x equals 1 and x equals 3. And this is the kind of final conclusion, but note this supporting work is definitely required as well. So that completes the 2 examples I wanted to cover in this video. If you turn to the next page in your note packet, you'll see another example using the definition of the definite integral. And I do want to go over one more additional example just to get that practice before we start to move on to other properties of the definite integral. So before viewing the next video, I would highly encourage you to go through that next example. Give yourself maybe say up to 10 minutes to put a limit on it and see if you can use the definition of the definite integral to evaluate the given definite integral. So with that, stay tuned and take care.